So we're going to pick up where we left off last Friday on recursion. And we're going to, well, first of all, can anyone tell me what recursion is or what a recursive function is? No one knows? Okay. Okay, it's a divide and conquer technique. How does it do it? Like, it's a recursive function.
Like you have a base case and then usually return function you return like the value or something, but in the recursive case you return a function back.
Right. So it's a function that calls itself, and it works by one, identifying a base case, which is the smallest subproblem that possible, and then in the other case, the recursive case, it tries to chunk the problem down into smaller subproblems and it then solves by calling itself. So we went over a few examples, and one of the things that we wanted to talk about is that for many problems, a recursive function can be written iteratively, or actually for most problems. So there usually is some sort of a subjective choice in how to write a function, and it really comes down to ease of understanding. So what we've done is we've taken a couple of the algorithms that we showed last week, and we've written them iteratively, and we also have the recursive version, and we'll kind of compare and contrast and kind of see where we would want to use a recursive function. So on the screen, on the left here, we have the multiplication version, the recursive multiplication that we showed you last week. It's a little different because it turns out there's a couple of simplifications you can make. But did anyone, well, can someone walk me through how this works? So what's my base case first? Zero, right? And so obviously when n is zero, we're gonna, if we multiply by zero, then our result is zero. Now, there are two recursive cases, and I'm not really sure how to explain this intuitively, but let's say that my n is positive, right? So I'm multiplying by a positive n. Well, then all I'm gonna do is take m and just add it to the recursive version of itself, n minus 1 times. That's kind of how to read that, right? And then, analogously, if n is less than or equal to 1, then I'm going to take negative m and add the recursive result of n plus 1 times m. It is not too intuitive, right? So if we implement it iteratively, though, I think it's a little easier to understand. Now, this is also a subjective judgment, so you might disagree. You're free to. Here's our base case. Again, n is equal to 0 or m is equal to 0, return 0. In this case, though, if we don't have the base case, then we're going to initialize a result variable. And then for n is greater than or equal to 1, we're just going to enter a while loop and keep adding m to result n times. It's a little bit easier to understand, I think, than the recursive version. And then same thing for, well, I have a bug here. Same thing for n is less than or equal to negative 1. All right, so I'm going to run the two versions of this function. All right, so here's a recursive version, and here's the iterative version. They both return the same exact thing. They both work in generally the same manner. It's just that in one case, we're using recursion to solve it, which I don't find too intuitive. In the other case, we're using while loops. All right. So in this case, in my opinion, writing this iteratively, it makes a little bit more intuitive sense. But in other cases, let's say good old Fibonacci, we can write the recursive version and then the iterative version. All right, so here's recursive Fibonacci. We have our base case, or cases, and then we have our recursive case, right? You can almost rewrite the mathematical formula from this directly. All right, now, oh, why is it? There we go. So here's the iterative version of Fibonacci. We still have our base case, all right, but when we get to what was the recursive case, we have to do a lot of bookkeeping. We have to save off of the previous Fibonacci, what we're currently computing, and then we have to iterate, get the next Fibonacci, and then save off the prior versions of it. This is all stuff that in the recursive version gets done for us by virtue of just calling another function. So this is an example of a case where your recursive version is actually a little bit easier to understand. Doesn't mean that it's more efficient, and later on in the class we'll actually use this to talk about complexity. But the left version, I think, is easier to understand than the right version. Are there any disagreements? If you disagree, I'm not going to bite you. So anyway, we can run this, and we can see that the output's identical. All right.
What's
X-range? Probably something I shouldn't have put in there. X-range is like range, except that it returns what's known as a generator object that you can iterate over. So that I don't have to explain that right now. Well, actually, we'll probably talk about it later in the semester. The difference is efficiency. Range will return an entire list to you, whereas X-range is a little bit more conservative in how it manages its memory for these purposes. But changing it won't make a difference in the program. And for program as simple as this, range is perfectly fine. I just use X-range out of habit. So we'll do one last example, and then we'll move on to a different topic. If I didn't mention it before, in problem set 4, recursion is highly recommended for the final portion of it. So it's kind of important you understand what's going on. Anyway, so remember we looked at bisection early on in the semester, and we showed you an iterative version of bisection. Right? This shouldn't really be unfamiliar to anyone at this point. So all this is doing is finding the square root of a number using bisection search, right? And we set our low and our high, get our midpoint, and we just keep looping until we get a value that when we square it is close enough to x. And on each iteration, we set our low and our highs, right? depending on how good our guess was. Now, the recursive version looks like this. It has a few more lines of code, and before I launch into it, did we explain default parameters to you for functions? So, all right, Python has this feature where if you have a function such as rec bisection search, you can specify that certain parameters are optional, or you can give default values to them. So let's just show a simple example so I can get past this. So So if I define this function, this one's really easy. All it's going to do is print out x. I can call it like this, in which case it's going to pass 150 in, and x will be 150 when the function's executing. See, I'm not lying. Or I can call it like this. And it'll be 100, right? So that's, in a nutshell, what default parameters do for you. They're useful in some instances, as in this example. So in this recursive version of bisection sort, or square root, sorry, we have a low and a high parameter that we specify. It's exactly equivalent to the low and a high parameter in this iterative version, right? And all we're saying is that if we're calling it for the first time, this is a common idiom for recursive functions in Python. If we're calling it for the first time, we're not going to specify in a low and a high. So low and high will be none going into this function, and then we just set them as we did in this iterative version. And then we set the midpoint, and then we have slightly different structure here. If the midpoint that we guess is close enough to the square root of x, then we just return the midpoint. On the other hand, if it's too low of a guess, then we're going to recursively call ourselves with the same x, same epsilon, but we're going to use midpoint for the low parameter. So midpoint, in this case, is here, and the same high parameter, all right? And then if we've guessed too high, then our low parameter is low, and then our high parameter is the midpoint. So it's doing the exact same thing as the iterative version. We have recursive, iterative, recursive, iterative. Same thing, just different forms. All right, before I leave recursion, does anyone have any questions? Or want to ask anything, or complain? No? All right.
Do you use a lot of recursion in your work? Like, do you normally use iterative or recursion? Or is it just case by case?
It's case by case. It depends on the problem. And what we were trying to show here is that there are some problems that are better expressed recursively and others that are better expressed iteratively. And by better, it's a very subjective term. It's, in my mind, it means more intuitive, easier to understand. It allows you to focus on solving the problem rather than filling with code. On the other hand, sometimes efficiency comes into play, and we're going to be talking about that pretty shortly. And in that case, you might want to do a recursive version because it's easier to understand, but it takes too long to run, so you write an iterative version. So computer programming in a lot of cases, actually in all cases, is a bunch of trade-offs. You know, oftentimes you'll trade off speed for memory, elegance for efficiency, that sort of thing. And part of the skill of becoming a good computer programmer is figuring out where those balance points are. So, and it's something that I think only comes with experience. All right, so we've talked about floating point, I think, to death, but we just want to really emphasize it because it's something that, even for experienced programmers, still trips us up. So the thing that we want you to understand is that floating point is inexact. So you shouldn't compare for exact equality. So looking at the code here, I've defined a variable 10/100ths, which is just 10 over 100, and 100th, which is just 1 over 100, and then 900ths, which is 9 over 100. And so in real math, this condition would be true. I add 100th and 900ths, I should get 10/100ths. So if we were not dealing in computer land, this would print out. But because we are dealing in computer land, we get that. All right? And the reason is because of Python's representation. Now, when you write print x, if x is a float variable, Python does a little bit of nice formatting for you. It kind of saves you from its internal representation. But you can look at, so here is 10/100ths, as you would just print it out. It's what you would expect it to be. But this is what Python sees when it does its math. All right. And it's not just Python. This applies for anything on a binary computer. It's an inherent limitation. And you know, we can get arbitrarily close, but never exact. And then, again, if we have 100th and 900ths, Python will show us 0.1. So when you print these out, they look fine. You know, if you were writing debugging code and you were wondering why, if you compared x to y, it wasn't exactly equal, you know, you would naturally print out x and then print out y, but it would look equal to you, but you know, the code wouldn't be working properly, right? Well, the reason is that the internal representation that Python is using to compare them is that. So, what's the solution? It's an actual question. I don't know the answer.
If they're close enough, then they'll make exact comparisons.
Right. So we're gonna say good enough, right? And the traditional way of representing that is epsilon. Epsilon, you've seen it in your problem sets and you've seen it in code before. And if you've come to office hours, someone's probably explained it to you. Epsilon is the amount of error we're willing to tolerate in our calculations. So in Python land, you can, I think, have arbitrary precision. Don't quote me on that, though. But for purposes of this class, if you're using an epsilon that's like 0.0001, we're not going to get too upset. All this function does, and this is a handy function to keep around, is it just tests to see if the distance between x and y are less than epsilon. If it is, then we say they're close enough to each other to be considered equal. So I don't like the function name compare. I don't think it's intuitive. Close enough is probably better. But it's also going to break my code. So. Uh-oh. This is an actual bug. Line 203. What did I do to myself? I commented out my definitions, is what I did. All right, so if we compare the two values, 10/100ths and 1/100th plus 9/100ths, and we use our close enough, our compare function, then yeah, it's within epsilon. Again, notice here that we're using a default parameter, so if we don't pass in something explicitly, so I can say something like this. Let's make epsilon really tiny. So if I make epsilon really, really tiny, then it's going to say no. So how you determine epsilon really depends on your specific application. If you're doing high precision mathematics, or you're modeling like faults on a bridge or something, you probably want to be pretty precise. Because if you have the wrong epsilon, then you might have cars falling off the bridge or the bridge collapsing, and it would just be a bad day. So, are there any questions so far about floating point? No?
You can only go as close as the error is.
What's that?
You can't get as close as you want. How can you make the error that small?
How can I make?
It's not going to get that close.
Well, yeah, that's what I mean. So there is a limit to how close you can get, and it depends on the language, and it also depends on the hardware. There are, and this is getting a little bit more technical than I want, but you can define pretty precisely the smallest value that epsilon can be. In a language like C, it's defined as the minimum difference between, two floating point variables. That's representable on the host machine's hardware. So, yeah, there is a limit. So there are some math packages, though, and we'll be using something called NumPy later on in the semester that allow you to do pretty high precision mathematics. So, just keep that in the back of your mind. But yeah, you're right. You do eventually hit a limit. Okay. So the last thing that I wanted to cover on floating point is that even though it's inexact, it's consistent. So let's say I define a variable 9/100ths plus 1/100th, and it's exactly what it says, 9/100ths plus 1/100th. Now we know that this is not going to equal 10/100ths, right? We've just demonstrated that ad nauseum. And also, yeah, I'm still defined. And the question, though, is if I subtract 1/100th from this variable that I've defined, this 9/100ths plus 1/100th, can I compare, will 9/100ths now be equal to 9/100ths plus 1/100th? So in other words, will this be true? And the answer is yes. And the reason is that if I'm adding or I'm subtracting, even though 1/100th we know is an inexact representation, it's still the same. And so when we do the subtraction, we're subtracting the same inexact value. So this appeared as a quiz question at one point. It probably won't this semester, but it's something to keep in mind. So, any questions on floating point? If you want to, if you're a mathy type and you want to, look up IEEE 754. And this will give you all the gory details about representation and mathematical operations on floating point. And if you don't, then don't worry about it. It's not required for the class. Okay, so the next topic we want to cover is pseudocode. So can someone take a stab at defining pseudocode for me?
From what I gathered, it's basically like you're just kind of writing out what you're planning on doing in like just normal English.
I wouldn't say it's normal English, but it's an English of sorts. So the idea is that, and a lot of the difficulty that programmers have with writing programs or new programs is that we don't naturally think in computer languages. You think in English, or well, you think in a human language. So what pseudocode allows us to do is to kind of be in the intermediate, right? We still want to develop kind of a step-by-step process for solving a problem, but we want to be able to describe it in words and not variables and you know, syntax, which sometimes what will happen is programmers will get so wrapped around kind of getting the syntax right that they'll forget what the problem that they're actually trying to solve. So let's kind of walk through an example. Let's talk about pseudocode for hangman. And because you've all done this on the problem set, I don't have to explain the rules, right? So what would be a good kind of English first step for hangman?
You should choose the word.
Yeah.
Right. So let's not be too specific. We'll just say select random word. Okay. Now, what would be another good step? Next step.
Display display the amount of letter, like the amount of spaces, maybe, like.
So display like a masked version of the word.
Yeah, exactly. Like hide the word but display it.
Hide the word but display it.
Or, yeah, but like decide the amount of spaces. You probably want to state how many letters are in the word at some point.
Oh, that's a good point. Where should that go?
That should probably be before the display.
Okay. So tell how many letters. All right.
Okay.
Now, what would come after this?
After display,
Yeah.
See how many letters you have to choose from.
Okay.
First time you
First time you don't, but you know, the nice thing about pseudocode is that we can kind of barf things onto paper and then rearrange them as we. It's sort of like brainstorming in a sense, right? You know, you're trying to derive the structure, and it's easier to do like this than to try and do it in code. So, but yeah, you're right. You don't have to. So.
I guess you would ask the person to input a letter.
Okay. For letter. And then what would come after that?
So then you'd want to check if it's check.
Check if it's in the word. All right. And
If it is, add it to the word. Or,
add, let's say, 2 correct letters, guess.
yeah.
Okay. And if it
then
isn't?
If it isn't, reject it. Just say like, you know. Oh.
Let's
Well,
say.
we do want to remove it from
So.
the options.
So if it's not, then we're going to remove from options.
Yeah.
So letters remaining. Probably want to tell the user they're wrong too.
Yeah.
And use up the turn.
What's that?
You want to use up the turn. I'm sorry.
And
You
use
can't
up-
guess as many
use up a
times as you
turn.
want.
Oh, yeah.
Yeah,
right.
if you have like a set amount of turns.
Okay, so we're actually going to get to that.
I set mine like really high on the game.
I actually played all of your Hangman games. It was quite fun. So again, yeah, you're right. So we have a number of guesses that are remaining. And the thing is that we know that the user has a certain number of terms. So we're probably going to repeat a lot of this, right? So at some point, we probably want to have a while. And we'll just say while, you know, we have guesses left remaining. By the way, the reason why I program computers is because my handwriting is horrible. So while we have guesses remaining, we're going to keep doing all this, all right? And then we're going to remove But is this the only stopping criteria?
No.
What if they win? So while they have guesses remaining and the word is not guessed. So this is in essence your Hangman program. It's English language. It's not easy to read because that's my handwriting, but it's kind of easy to understand at an intuitive level, right? So, and the reason why we're talking about this is because we're going to get to some more complicated programs as we move through the semester. And a good starting off point for a lot of you when you're trying to do your problem sets is, you know, instead of trying to jump right into the coding portion of it, to sit down with a piece of paper, index cards, or a whiteboard and kind of sketch out a high-level view of the algorithm, all right? And so that we can see this in kind of code form. So let's say that I want to write a function that tests a number to see if it's prime. First question is, what is a prime number?
Factors are 1, so.
Right, so yeah, a number that is only divisible by itself in 1. Are even numbers prime? Can they ever be prime? Really? What about 2? Right. So 2 is one of our special cases, all right? So what would be maybe a good starting off point for pseudocode to test primality? Knowing those facts. All right, so can I erase this or should I leave it up? Because I can go over there. All right. It's not like I'm erasing any deep, dark secrets. There's no magic here. All right, so test number if what equal to say what 2? Yeah, why not? And maybe 3. Now what do I do if it is? Are they prime? So I'm done, right? So I'm going to return true. Now, what do I do if it's not, if the number given is not 2 or 3? You're talking about the modulo operator, right? So, yeah, we will use that. That will tell us whether or not an integer divides evenly into another integer, or the remainder after an integer is divided into another integer. But, well, let me ask another question. What is the maximum value of an integer divisor for a non-prime number, so for a composite number. What's that?
Number itself.
Okay, excluding the number itself. Well, let's say that I have n as the number I'm testing, square root of n, because I'm not going to have a factor that's larger than that, right? So, and I ask that because there's a loop involved. So, how would I go about this systematically? Well, I'd probably start at, let's say 5, right? Okay, and then test if n modulo, let's say 5 is equal to 0. Now, if n is evenly divisible by 5, then that must mean that n is composite, right? Because 5 is a factor. So, if it is, then return false. Okay. Now, what if it isn't? So that means that n is not evenly divisible by 5. Does that mean that the number is automatically prime? So what's it, after 5, what would be a good number to test, to move to? All right. 6? No. Yeah, that wouldn't be it, right? Because if it's divisible, or if it's if 6 is a factor, then obviously it's not. Well, yeah, whatever. So we're going to move on to 7, right? So basically, we're going to test all the odd numbers, and this is going to be the same as that. So this repetition indicates here that I probably need a loop, right? So instead of doing this, I'm going to say x is equal to 5, while x is less than, we're going to test if x evenly divides n, and if it does, return false. And if it doesn't, then we just increment x. And repeat, all right? And what happens when x becomes greater than square root of n? Well, the while loop's going to stop, and that also means that if I've made it to that point, then I've not found any numbers between 5 and square root of n that will evenly divide n. So that means that n is prime. So if I translate this into code, it would look something like this. Now, I see. So first, we're going to check if n is less than or equal to 3. If it's 2 or 3, then we'll return true. If it's not 2 or 3, then that means it's 1 or 0, right? So return false. So we've got those cases. And then we're going to iterate, or if n is greater than 3, we're going to iterate. Now, why would you go from 2? I don't know. We're going to iterate through all the possible divisors and check for divisibility. And if we evenly divide it, return false. And if we make it through the loop, we return true.
Does the return stop the loop?
Yes. Because, well, think about what return is doing. You're in this function test primality, right? And as soon as Python sees return, that's telling Python to kick out of the function and return whatever is after the return statement. So this false here, you know, it says return false. That means that it doesn't matter where you are, it's just going to kick out of the innermost function, or the function that encloses that return, and return that value. Any questions? All right. So testing primality, 1 is false, 2 is true, 3 is true, 4 is false, and 5 is true. So it looks like the program works. And if no one has any questions, I'm going to move on to the last major topic. All right, everyone's good on pseudocode? All right.
The main purpose of pseudocode is for yourself when you're writing a program, or when you want to explain something?
Both. So the question was, is writing pseudocode useful for just understanding a program yourself or for explaining it to other people? The answer is both. I don't know, it's the difference between showing someone the derivative of a function and then explaining that, you know, what you're doing is finding a function that gives you the slope of the function at that point. So it's, you know, one is more intuitive for some people than the other, right? A mathematician would understand the former pretty quickly. An English major would understand the latter, maybe, right? So like when I explain my research to people, I don't tell them that I mess around with Gaussian mixture models and hidden Markov models. I tell them that I'm trying to figure out how people mispronounce words when they're speaking foreign languages. A lot easier for people to digest. With debugging, what are bugs? Mistakes. And if you see one bug, there are probably many more, right? All right, so when you're debugging, your goal is not to move quickly. This is an instance where the maximum fastest slow and slowest fast comes into play. You want to be very deliberate and systematic when you're trying to debug code. You want to ask the question why your code is doing what it does. And remember, the first recitation I said that your program or your computer is not going to do anything that you do not tell it to do. It's not something that people do naturally. Like if you watch some of the TAs, and you know, sometimes a student will say, how do you find the bugs so quickly? Well, it's because I've been programming for 18 years. Professor Gutag's been programming for longer than that. So a lot of it is experience. And it's just, you know, when we've debugged our own programs and when we were learning to program, it was as painful for us as it was for you. So that said, you want to start with asking how could your code have produced the output that it did. And then you want to figure out some experiments that are repeatable, and that you have an idea of what the output should be. So after you do that, then you want to kind of test your code one by one on these different test cases and see what it does. And in order to see what it does, you can use a print statement. So when you think you found a bug and you think you have a solution in your code, you want to make as few changes as possible at a time. It's because as you're making corrections, you can still introduce bugs, right? Let's see. A useful way to do this is to use a test harness. So when we actually grade your problem sets, a lot of the time the TAs will put together a set of test cases for your code. So one of the things is a lot of the times when you get one of the problems, or when you look at the problems, it'll have some example input and output, but that doesn't necessarily mean that we only test on that. There's additional test cases that we use. And it's not to trip you up, it's just because there's a lot of different variations. And it's also, if you read the specification and you follow the specification, then you'll be fine. But moving on. So let's look at an example. I have a function here, is palindrome, all right? I think you've seen this before, right? Yes? Yeah, okay. So it's supposed to return true if string s is a palindrome. And so I've written this function, and I've also written a test harness. Now, there's a lot more code in the test harness, but it's pretty simple code. I'm going to think of, when you're writing functions, you want to think of the type of input you could receive. And you want to think of what are kind of the boundary cases, so the extremes of input that you can get. We call these boundary cases edge cases. For the is palindrome function, it would be like the empty string would be one, or just a single character, right? These are kind of the minimum we can have, or we could think of. On the opposite end of the spectrum, we can have theoretically, we could have an infinitely long string. So we're not going to actually test for an infinitely long string. So anyway, all we're going to do is, in our test harness, we're just going to run the function on these inputs. And we know that an empty string should be true. We know that a single character string should be true. We know that, if I have a string that's 2 characters long and they're the same character, that should be true. If they're 2 characters, then it should be false. And what I'm going to do now is I'm looking at kind of what we call expected input. So after I've hit my edge cases, I'm going to look at all the strings of an even length and make sure that the function works properly. And then I'm going to look at strings with an odd length. And then once I get to this point where I've tested a number of different lengths, and in this case it's just 2 through 5, or 0 through 5 if you want to include the edge cases, then I'm going to say, well, it looks like all tests are passed, and I think that this function works pretty good for anything we can expect it to encounter reasonably. So the way that you kind of use test harnesses is you want to, every time you make a change to your program, you want to run the test harness, because that'll catch any bugs you may have introduced. And so I'm going to finish up with this really quickly because I know my time's up. So I got a bug, right? It's telling me that one of my test cases failed. So line 299, which is this test case. So what we can do is, now that we know that fails, we can say, maybe print out our input and see what we have. And instead of just running, I'm just going to run that one test case that failed. Okay, so obviously this should be true. And what we're seeing is that on the first call to is palindrome, S is ABBA, and then on the recursive call to it, we only get BBA, right? That means that we've only chopped off the front character, right? So you see the bug? Well, here, right? So, there we go.